Okay. Well, good morning, everybody. Thanks for coming out. My name is Scott Holder. I work for Alpha Laval, which we've got several projects that we're working on with UCC and these guys as well. So we know each other pretty well. I cover zero liquid discharge applications. I cover evaporation and zero liquid discharge and minimum liquid discharge. Minimal liquid discharge is MLD is the acronym. It just means concentration, right? So zero liquid discharge going all the way down the side. So I cover that for Alpha Laval. Alpha Laval is an industrial heat transfer is our primary business around the globe. We're based in Sweden, been around over 100 years. We have a lot of other different products, but our main focus is industrial heat transfer. And you'll see us in almost every plant in the country in some fashion. So I'm going to talk about zero liquid discharge, and specifically we'll go into a little bit of flue gas desulfurization, some of the new rules that are coming out, which are going to be pretty important to power industry. This talk can be taken for any industry as well. So what we're talking about today can be transferred pretty easily to other applications. The first thing, zero liquid discharge, why it's all important. We all know these numbers. They're pretty easy to understand as well. Most of the water on Earth is salt water. Of the fresh water, very little it is actually accessible for us to use. So water conservation and water reuse are really important factors for any industry, and specifically if there's legislation coming that's requiring this, also depending on the region of the world you're in. What drives ZLD, again, we know these, water recovery, especially in places where water is a very scarce resource. So even in the U.S., you have the western states see it much differently than the eastern states, specifically in power as well. Waste minimization, ZLD can be used to reducing volume of wastewater coming in, so you can evaporate off the water and take out volume and still leave a slurry or a highly concentrated solution for disposal. Product recovery, so even in this, we're going to talk about waste streams, but this is actually very valuable in process streams as well. One of the large industries we're in is lithium, using the exact same technology to crystallize salts, lithium hydroxide, lithium sulfate, for battery grade lithium that goes on to further processing for battery. Drivers, and here is really, legislation that's driving these changes in the power industry, which is really important for us to focus on. Net zero, some of these industries are adopting these programs themselves. Treatment costs, storage costs, all these are kind of starting to, the importance of ZLD over the next few decades is only going to increase, my opinion, and it's going to increase substantially over time. So understanding these technologies, what they're capable of, you even had in your slide, evaporation, which I'll go into a little bit. I guess first thing, understanding with ZLD, this is thermal separation. David was talking about physical chemical separation. And in ZLD evaporation, you're mainly targeting the dissolved solids. So you will you'll concentrate past saturation, you'll form crystals, salt crystals, and then those will come out of solution and you'll remove those and dewater them. So for this application, thermal transfer, the thermal separation, and mainly focusing on TDS as the main culprit. So you'll use traditional, which I'll go into in a minute. So here you have your plant process, and this can be, one main thing I really point out. We always have this process flow chart, and it's pretty linear in most applications. Power plants, you're going to be taking, this would be the flue gas water coming out, wastewater coming out, and we go into our ZLD system, and I'll go into this a little bit more. Here, the water evaporated off, gets recondensed, so we're not evaporating anything to the atmosphere. So all this goes back into another plate frame heat exchanger that we make, gets condensed and sent back to the plant for reuse. I'll go into, in a minute, quality and what to expect with those systems. Then salts get dewatered and sent to landfill or disposal. Again, the main thing here is to understand there's a difference. There's chemical, there's physical separation, then there's thermal. Thermal is the most expensive form of separation because the energy required to put in it. So this slide here, this is what I would say is a typical process layout. As with RO, you're going to want pre-filtration, softening in front of your evaporation systems. And I'll go into, we can talk a little bit, but try to keep this kind of on track and moving. You know, our systems can handle suspended solids in the feed, and I'll go into why we do that and can. This is a typical process flow for a wastewater plant. You have the water coming off, you have different types of mechanical and physical and chemical treatment through here. Then you've got biological, RO. We're taking the RO reject. You just mentioned what, this is unplanned, by the way. What to do with the RO reject. So, and I've got some mass balances and flows here in a minute, you'll see. So you can have 1500 GPM and you can still have a substantial amount of reject, highly concentrated salts, and even some TSS or RO, it won't be TSS, but highly concentrated TDS. That's what we want. We want the highly concentrated, highly corrosive, you know, ideally you don't want high fouling, and there's ways to handle that. But that's the waste stream that the evaporation systems are going to take through ZLD. I want TDS as high as you can get it. 20%, 30%, 30% would be at past saturation. But so that then the strategy is to basically use as much existing off-the-shelf technology before you get to our system to reduce the volume you're having to treat, thus reducing CapEx and OpEx through energy. And I've got some more mass balances and process flows. One thing here, this does not have to be a linear placement either. You can put this zero liquid discharge right there if you want it. If you had a highly concentrated waste stream coming off, before you commingle it in your wastewater, I always encourage customers, if there's a way to pull that trouble, because typically there's one or two waste streams in a plant that are causing the problems for the wastewater plant. I want that before it gets commingled. That's not always possible, and in this case, it's probably not possible. But the main thing is when you're looking at these systems, is to think out of the box. What's causing me the problems, and can I pull it? And the other thing, too, is I'm not going to spend a lot of time on, but since we're a heating transfer company, we make gasketed plate heat exchangers. We're the largest buyer of sheet titanium in the world. We're the largest distributor of plate and frame heat exchangers in the world. I also want to be located to where any waste heat is, because I can use waste heat to evaporate the water. And that's a very real, very, very real proposition. So if I'm at the end of the wastewater plant, sometimes it is so difficult to get waste heat that maybe you're sending to cooling towers or other processes. I can pull that heat out of the fluid, send it in, and help this. So just keep in mind that you don't have to place your ZLD system at the very end of your process. Technologies, which you covered a little bit for me, David, that go in front of ZLD. Obviously, softening, because you will have scaling. Scaling and fouling are probably the biggest concern of people looking at this technology. Having said that, there are ways you can handle it. If you have a high scaling or high fouling application, you can always look at softening in front of it. That does a lot in the projects we have with UCC. Those are all the things we're looking at. You can look at selective type of membranes. You have RO here. This is for concentration. One of our partners that we do a lot of work with is this company out of Reno, Nevada, called New Logics. They make a VSEP membrane, which is written into the EPA rule for flue gas. I've known these guys for years, well over a decade. Their products are pretty unique. This membrane is an RO membrane. They also have the UF membranes, but they can handle, they don't foul. And that's, the entire membrane surface oscillates, vibrates, and thus it's very similar to cross-flow filtration where you have movement across the membrane surface, preventing fouling. So this technology is actually written into the EPA rule as preferred technology or best available technology to do this. They work great with us, Unique feature too, this membrane can handle suspended solids in the feed. And that is what makes it different than all other membrane technologies in the world. So that is, they can remove scaling ions, pre-filtered. Now, those scaling ions are going to be concentrated, and I'm going to take those, right? And I'll talk a little bit about how we handle scaling inside our systems. But basically, my point in this slide is you're going to need lots of different, you want to look at all the different applications. ZLD is not the end-all, it's not the silver bullet, it's a component, it's an arrow in your quiver, right? Yeah, that's right. Yeah. So it's not a standalone. It can be a standalone in some applications. The evaporation system, you're going to get your water back. It's going to be condensed, recondensed, and go back as processed. Typically, the distillate coming off these systems, you can expect 50 to 100 ppm of TDS. Sometimes you get more. It depends. We can get down to 10 to 20 ppm of TDS in the distillate, depending on the application and how we configure the separation vessel. Your solids coming off will go into a decanter for dewatering. I'll show you some slides on that, some pictures here in a minute on that. Types of systems, there's 3 types of systems. Mechanical vapor recompression. Most of the time this is where people want to go, so they don't have excess steam or enough waste heat to run the system. If you're going to run with steam, you either have to have excess steam or the capacity, or you put it in a boiler, then it starts to run. So mechanical vapor recompression, we use a mechanical vapor recompression fan that drives the evaporation. So this is a one effect. So this fan is the energy we're putting in. So as the system starts up, it starts evaporating. You're going to produce your vapor coming off the top that gets recompressed with the blower and sent back into the system. So they're pure 100% electric, minus a little bit of startup energy. Thermal vapor recompression, this is medium pressure steam coming in to our system. Obviously, the customer has to have this. And then we pull a certain percentage of the steam coming off the first effect and recompress it through this. This is a basic, kind of looks like a venturi, but it's a full piece of, there's no moving parts to it, so it's very, very inexpensive to run. And then you add multiple effects. And then we have multiple effect steam or waste heat. So this can be waste heat we're pulling from another part of the plant through a heat exchanger, right? Send that in. And we can evaporate systems. Multiple effects are used to reduce your energy costs, so every effect you add reduces the required input of energy. So 1 ton of steam will evaporate 1 ton of water in the first effect. By adding a second effect, 1 ton of steam will now evaporate 2 tons of water. It's a rule of thumb. So, and obviously it works in reverse as well. So that's where you start looking at CapEx versus OpEx, and those calculations can be easily done. The kind of case study I want to talk about today is actually a produced water case study, but the water chemistry is extremely relevant to flue gas desulfurization. You're going to have all the same constituents in it. This is actually a hydros. This is a produced water facility, pure 100% ZLD facility in southern Italy. We commissioned this plant about 2 years, not quite 2 years ago. 8 tons an hour evaporation capacity. So in evaporation, we're talking tons of water evaporated, not GPM, not barrels or anything like that. You can do the conversion pretty easily. So 8 tons an hour capacity, the feed coming in is 10 to 45%. TDS, installed southern Italy. That's actually a picture of the facility. This was actually a picture of the install. That's the diagram, and that's the actual install there. Again, you see the process layout is very similar to what I had before. They have lots of clarification. They have biological treatment to get the organics out. You want the organics out. That will affect your solids quality and crystallization. And then they go to RO. We're taking this highly concentrated waste stream straight into our evaporation system. The feed coming into the plant is 100 cubes per hour. I'm not going to do the GPM conversion because I have 144 GPM, and we're going from 100 cubes an hour of feed, and what the evaporation system is getting is 8. So it's a significant reduction, right? And that's typically what you want to look at. And in flue gas desulfurization, it's the exact same way. You want to take as much of the used conventional clarification and that concentrated waste stream is what we want. You see the water chemistry here, sodium. That is not very good on the eyes. Lots of magnesium, high scaling, high fouling applications. Materials of construction of this are titanium. So it is corrosive, but we have, like I said, lots of materials of construction. We go up to nickel, PD, titanium, and those alloys. Hastelloy and stuff. But in this application, it's going to be titanium. And in here, we're not going to go into an entire thing on scaling and fouling. There are lots of ways to handle scaling and fouling. Without getting into a lot of detail on our system, we use a process called forced circulation. So as the system is coming in, as your system is recirculating inside our plate and frame heat exchanger, we're using high velocity, and we should have brought some of the plates. I don't know why we didn't. And the plates are more like corrugated. They have a lot of geometry on them to create as high a shear force as possible. So what I typically, how I explain this is, if you're familiar with ultrafiltration, crossflow, tangential is the high velocity across the membrane surface. It's helping shear the surface of the membrane to keep it clean. Exact same thing's happening here. We're just not a membrane. We're keeping high velocity across that plate with a recirculation pump, and the geometry of the plate is designed to create turbulence. We crystallize inside our plate and frame heat exchanger. So there is no crystallization phase. And what that does, as those crystals start to build their self-cleaning mechanism, they're soft, they're not hard, so they're not going to do a lot of erosion on your plate surface. But the salts, as we crystallize inside, they're helping keep the plate surface clean. Okay, so if there is scaling and fouling, the benefit we say for plate and frame is you can open them up and clean them. Depending on the plates, depending on the size, you could probably open these up, either replace the plates, do your own cleaning later, or clean the plates, put them back together in half a day. Easy. 2 people working. So you have that accessibility. You also can add anti-scaling, which, again, going back to volume and stuff, is a lot better to treat 8 cubes per hour than 100. So that works really well. And then the way you run the system and the temperature, we also can evaporate at atmosphere or below atmosphere. So a lot of times we'll take the water chemistry, model what's going to precipitate at what temperature. We can select a temperature that will keep certain things in solution and certain things that won't be in solution, right? Or it's precipitating out. So we can control that. And then if you know the scaling ions, you obviously can go to pre-treatment ahead of time. But again, it's a complete solution. You have to look at it holistically. It's not a black box you set at the end of the year thing. I wish it was. It's just not. This is the mass balance and process flow. So this is the thermal vapor recompression. So you have makeup steam coming in, first effect. And you'll see these here inside a thermal, when you're doing zero liquid discharge, any type of thermal separation, maintaining and recovering all the energy in the system is really critical. Not only for operation, but just economics. Power, we might overlook some of that because of the relative availability of power. It's still important to recover. So we have preheaters here. So you'll see the condensate coming out is actually used to preheat because it will come out close to evaporation temperature. Say if we're, I don't know, what do we evaporate? I can't read those, too blurry. Say if we're evaporating at 80 C, well, that distillate coming out is going to be really close to 80 C. And we want to use that to get the feed up as close to 80 C as we can going into evaporation, because we want the evaporator to be the energy going into actually evaporating the water. The other thing we do to reduce scaling and fouling, we do not evaporate inside the plate heat exchanger. There is no evaporation, so you won't have evaporating on a surface, will create scaling almost on everything. So there is no evaporation. We flash evaporate inside this vessel. So forced circulation, flash evaporation. I forgot to mention that earlier. This is not my normal presentation. I've got a lot more illustrations on that, but 15 minutes goes by quick. Second effect here, the distillate finally goes into your condenser. That you can see the process flow comes back in. It's actually, we use the incoming to cool down your condensate and to preheat your feed. Then that comes out, that goes to process. In this case, I think they're right around 100 to 150 ppm of TDS, which is not ideal. But we know that the main reason that was coming over was carryover from foaming. So this vessel is designed for separation. You want your vapor going up, you want your water coming down. So these are pretty tall vessels. And if you have some carryover micro droplets that are getting pulled with the vapor, we put it in demisters. In this application, I think they used some anti-foaming, and that solved their problem. But again, 150 ppm of TDS is cleaner than anything coming into the plant, so still very manageable. We typically will say 50 to 100, but we can get it down to 20 with demisters and the right kind of stuff. Solids coming off, they were 90 to 95% dry, which is pretty good for salts. Let's see here. There we go. So this application, the salt quality changes as the customer comes in, so there's variation in the feed. The salt some days will be red, some days it'll be white. So keep that in mind. They can handle variations, and the process is designed for it. And I know in flue gas and coal plants, you'll have different types of coal coming in as the same kind over time, but you'll have different sources. So that is something that they can handle. Alright, so that's that. Going back to some of the technology, I'll cover real quick, just go over this real quick and then I'll be done. This is a mass balance form of the VSEP RO membrane. Again, I want to show you that equipment, when you think ZLD, you want to reduce the volume going into the evaporation system. It's just pure economics. Just the energy putting in to evaporate is so high. This is a feed coming in. This is an FGD application. I can't, sorry, this is so tiny on here. It's not gonna, we'll just high level. So basically, yeah, feed coming in. This is the reject stream. So I want the reject. So this is literally what goes to the evaporation system. You have the permeate coming from, this is probably a stage 1. This is probably ultrafiltration. I mean, it actually is. And that will pull out all of your larger ions and stuff that comes out, maybe a loose RO. That will then go on to a next stage of RO, and then you'll go, final stage will be a spiral. But in this, you get your reject, comes back, goes to the feed. This is the reject that I'm taking. So you can kind of see, you can take this from, what is that, 155 cubes down to 29. Yeah, so it goes into the size of the system. This is a very compact, easy system to use. We make fully turnkey systems that are plug and play. We use we're Swedish, so we always talk about IKEA. So we assemble the plants in our factories, disassemble and put them in containers, and they show up on site for people like you to put together. Right? So this is, again, this is mechanical vapor recompression instead of thermal vapor. So the only input is to start this up. When this says some incoming steam, if you don't have steam, we just put electrical preheaters in there and you run it. These systems are extremely easy to start up, shut down. There's no additional labor. You'll have one person monitoring it in an MCC. That's it during the day. An hour, 30 minutes to start up, hour to 30 minutes, and an hour to 30 minutes to shut down. Plates, we have hydros. They ran 6 months, opened up their plates to inspect them, change their chemical program a little bit, and go from there. We have customers that have been running these for 3-4 years and they never even open up the plates. So you can also tell when your flow, there's instrumentation on there that will tell you when you need to go into it. So Questions? That was a lot. I talked fast.
When you go into a shutdown, do you struggle with material precipitating where you don't want it to? Or is that?
If you do it right, you won't. So when you're shutting these down, you obviously have high concentrations, you have saturation. There's obviously drains at all the low points. You want to drain it. Sodium chloride is not as big of a deal. Sodium sulfate, that's bad. Trust me, I've been there.
Yeah, me too.
So there's just flushing it. You're going to come in, and even there's CIP built in as well, which I didn't cover. CIP, you just isolate the heat exchanger, add your CIP chemical, and you just recirculate for 30 minutes to an hour, and then drain that, fill it back up, and start going. So you're not evaporating. So the way the systems are done, shut down, a lot of customers have a couple of manual valves. They go out there and change. You can do automated, but it's up to you. You'll drain the system. Ideally, it's really good to flush the system with fresh water. Just if you're shutting it down, clean it at the same time, and then all the lessons learned from customers that buy the components with themselves. You want all your low level, your dips, and all the low lines to have drains on them, all of them, which we designed that in as well. So, other questions? Anybody? Let's go. Well, I'm around as well. I've got cards. If you want, happy to chat. We'll be here. So,
Thanks.
you can close.